Last time we left off with the beauty contest. Initially, this is a actual newspaper contest where they showed 6 pictures on the newspaper and asked everybody to send in a postcard nominating one of these beautiful pictures. And so one of these candidates. And the goal was to be to choose what everybody is choosing. And so John used this example as as a metaphor of the stock market, saying that what you should not do is just pick what you think is the prettiest. Instead, not only you should not think about being which is the prettiest, but also not just a naive idea about what the average opinion is. Now you should be smart enough to go to the 3rd degree and say, wait a minute. What's the expectation of the average opinion of who's the prettiest? And of course, you can go beyond this and say, wait a minute, what about expecting the other people's expectations about the average opinion, and so on. You can go all the way up. And so it's like the stock market in the sense that, well, recently the market has crashed. Should I buy tomorrow morning? And of course, that depends. That depends on how other people think. And so predicting whether or not you should buy or sell today is like predicting what other people are thinking or are going to do at the same time. And so you basically, because if everybody thinks that, oh, the prices are so low, I should buy, then you should buy now, immediately, to be ahead of everybody in order to gain from this bull market. But if everybody thinks that, oh no, China is going to collapse, the world economy is going to collapse with it, and so on, then what you really want to do is to sell now. And so this prediction about what the average opinion on the market is the essence of how to buy low and sell high on the stock market. So to sort of mimic this idea, so what we designed is this, what we call the P-Beauty contest, or sometimes it's called the 2/3 of the average game, which is you are allowed to pick one number between 0 and 100. If you want, you can pick pi, 3.1415926.5, whatever. And the goal is to be closest to 2/3 of the average. So if the average is, say, 60, then 2/3 of that is 40. So you want to be as close to 40 as possible. So now it's your job to write down a number on a sheet of paper and sign your name on it. Okay, so your goal is to be as close to 2/3 of the average as possible. So what would you want to pick? Yeah. Well, that's the challenge, right? It depends on what other people are picking. Okay, so I also provided an answer here. I will list this on the blackboard during the break. But let's put this here and think about this question first. How much should you pick? Think of this carefully. Suppose everybody picked the maximum, 100. What is the average? Well, the average is 100, right? If everybody's picking the maximum. Then what is 2/3 of the average? Well, 66.666667 or whatever. So what this means is that if you picked, picking 67 is definitely better than picking 100. Why? Because even if everybody else is picking 100, 2/3 of the average is still closer to 67 than it is to 100. So what this means is that if you are picking beyond 67, you must be stupid, or you did not consider carefully. Okay, let's ask, how many people picked above 67? Nobody. Okay, so you guys are at least not that stupid. Good. Wait a minute. Should we stop here? No. So if you believe that everybody is that smart and that you will not be too stupid to pick above 67, then what is the maximum of the possible average? Well, even if everybody's picking 67, well, the average is 67, and so 2/3 of that would only be like 44 or 45. So then you should not pick above 45, because picking 45 is still better than that. How many of you picked above 45? Okay, one person. Okay, well, okay, so now you immediately see somebody is not as smart as you. Wait, but is that a right statement? Maybe not, because you can go on, right? If nobody is picking above 45, the average cannot be above 45, which means 2/3 of the average cannot be above 30. How many of you picked 30 or beyond 30? Yeah, okay, so you might say, oh, so he's dumb. But wait a minute, you're as dumb as well, unless, because this idea can go on and on for infinitely many rounds, and so there's only one possible smart answer to this question, to this game, which is picking 0. How many of you picked 0? Okay, so we do have one ultra smart lady that picked 0, that picked the only one correct answer. Everybody else is actually equally dumb, because this logic can go on and say that you should only pick 0.
But it's only the best answer if you expect everyone to.
Oh, yes, that's the problem. Yeah, so it is true that this logic leads to only one answer, but if there are some other people who are not as smart as you are, or who do not expect other people to be as smart as everybody else, then picking 0 may not be the right idea. It's like the joke that there was this famous person who predicted that, oh yeah, so the stock market is a bubble back in 1999. But too bad. I mean, the bubble burst in 2001. He was way early. So that may not be. So even though in hindsight you say, yeah, it was a bubble, but picking 0 when other people are not equally sophisticated as you are may not be the right idea. And so, we will wait to see the results. But given, okay, let's do a quick survey of how much you picked. How many of you picked below 10? Okay, some people picked below 10. How many of you picked between 10 and 20? Okay, some of you. How many of you picked between 20 and 30? Okay. And how many of you picked beyond 30? Yeah, so a few people. Okay. So here you see there's a distribution here. And so it's likely that 0 will not be the winner. It will be somewhere in between, maybe between 10 or 20 or something. But well, that's an empirical question we have to decide. We have to figure out. But so the fun thing here is that the theoretical answer to this game is that there is only one unique Nash equilibrium where everybody is picking 0, and so it's like a random draw. And this is what we call a dominant solvable game because we got to the answer 0 by deleting dominated strategies. First above 67, then above 45, and then above 30, and so on, going all the way down to everybody picking 0. Of course, empirically, the question is whether or not people actually all pick 0. And as you just saw, even in this class, that's not the case. People have run this in numerous experiments, and the average, first round average is usually between 20 and 40. So yeah, and of course here that depends on the group of the population. It depends on say which major you are or which university you're in, and so on. They even run this on newspaper or magazines, and so it depends on the population of that city or that country. But it's usually far from 0. Although, if you play this, like say twice, a third time, within 10 rounds of repeated play, this converges to 0 fairly quickly. So you know that it's not that the equilibrium is not the right prediction. It's not the right prediction for an initial response. And so what this means is that here, here we do confirm that the equilibrium is a good prediction if we have repeated play of the same game. But what's remaining a puzzle is how do people pick in the first time? That's one question, especially when you do not know other people's, how other people are thinking. The second question, of course, is knowing the results of the first round, how would you update your guess in the second round and the third round and so on? So that there is room to develop a learning theory about how do we actually converge to the equilibrium. All right, let me show you one class result. I did this back in 2008, and so this is a distribution. There are some crazy guys over here who purposely picked 99, 89 or something to ruin my experiment. However, even counting these guys, the average is 27.75. Taking those guys, so the target, 2/3 of the average is 18.5. Even dropping these crazy outliers, average is close to 21, so 2/3 of the average is around 14. So yeah, so even with these crazy guys trying to ruin my experiment, well, you see that the overall conclusion of the experimental results still hold in the sense that, yeah, so the range, so first round, it's almost surely never close to 0 between 20 and 40, but there's an interesting variation here. Yeah, and you guys, well, yeah, so maybe the average will be smaller than this. That's my guess, based on my quick survey, but we'll see the answer after we review it. Okay, so the last example I'm going to show is Continental Divide. So the story of this is to imagine an industry and where do you want to locate this industry. Suppose you want to start a new company, a new online business. Where would you want to start this company? Will you want to go to Hollywood? So here it really depends on the characteristics of your business. If you also want to start this online sort of app business, then it's possible that you want to do this in Silicon Valley because that's where all of these, the expertise is. Just like if you want to start a movie company, unless you're George Lucas, who insists on establishing the Skywalker Ranch in Northern California. Otherwise, most movie business is in Hollywood. So when you actually start a business, there could be a lot of factors to consider. You might not want to start the same place as where your competitor is, but also there could be a knowledge spillover, or because the customers are familiar with this type of business. So you might want to start closer to your competitor. But if you think of an industry as a whole, there could be a clustering effect. One of the best examples would be that all of the high-tech industries in Taiwan are clustered in the Hsinchu Science Park. They have this joke that regardless of whether or not this tablet is branded as a iPad or these the phone pad or these other Android tablets, they're all designed in Taiwan. Well, that's not exactly true. Now some of them are done in Samsung in Korea. But what you do see is that so a lot of these companies are clustered in the same area. Be it, and the same thing applies for laptops, right? I mean, regardless of its HP, it's branded as HP, as Dell, or as Acer, or as even the Apple. I mean, all of these are designed in Taiwan and now assembled in China. And even in China, you have this cluster. Oh, it's all in Dongguan or in these special regions. And one of the reasons is because there could be a lot of positive spillovers here. Even though these firms are competitors in the industry, but because of the knowledge spillover, they still want to be located at the sort of close to each other to actually gain from this kind of knowledge spillover. Okay, but what this means is that sometimes it's really a matter of history why things are here or there, because it could be just because it happened this way. So one story of why all of the movie companies are in Hollywood is because the advantage for Hollywood is that, well, it never rains in Southern California, which is very good if you want to film outdoors. Well, you can create artificial rain, but it's very difficult to create artificial sunshine. So yeah, and because of that, so that once the first few movie companies are stationed in Hollywood, then everybody else wants to be close to that. And of course here that could be a clustering effect, because if you are an actor looking for a job, then shopping around Hollywood would be a good idea. And of course, knowing that a lot of actors are shopping around here, you as a writer, a director or screenwriter would also want to cluster here. The same thing applies for marketplaces as well. If you go to China to buy something online, where would you want to buy? Taobao. Where else? Where else? Jingdong. How many people heard of Jingdong? Okay, so a few people. Okay, what about number 3? What? Alibaba owns Taobao. Yeah. Yes, maybe Amazon. Now we have Amazon. Yeah. But what you see here is that there's a huge cluster of where do you want to buy and sell things. And part of the reason is because, well, if you are a seller, you want to find a place that has the most buyers. And if you are a buyer, you want to find a place where there are the most sellers selling. And so there's a clustering effect where, so you really want to be where everybody else is. And of course, what this means is that, well, it just happened that it's Taobao because Taobao started at the right time and clustered, got the critical mass, and so on. And what you see in different countries is that people cluster on different websites. In the US, it used to be that eBay is very huge, and then Amazon is also big. But in Taiwan and also in Japan, it's Yahoo. For reasons, that's not very sure. Well, for mostly historical reasons. Let's put it this way. Actually, eBay established eBay in Taiwan before, but they eventually went out of business. So yeah. Okay. So how do we model this in a mathematical game? So here we have this game which is called Continental Divide. You're basically stationed in a groups of 7, where you pick a number between 1 and 14. And so your payoff depends on your choice and the group median. So it depends on how other people pick, or the median of the whole group. And the feature of this game, I'll show you at least most of the payoff table in the next slide. But the feature of this game is that if everybody's picking small, you also want to pick small. And if everyone wants to pick big, you want to pick big. So it's like the question, so when everybody's going to China, would you also want to follow? Or do you want to somehow be different? Okay, so let's take a look at the payoff table. So I'm not showing the extreme numbers of 1, 2, and 13, 14. But take a look. So here, this is your choice, and this is the group median. So if the group median is 3, you pick 3, you get 60. If the group median is 3, you pick 4, you get 58. If you pick 5, you get 52, and so on. And so if everybody's picking small numbers, you pick a very large number, you might get negative. But on the other hand, if the group median is 12 and you pick 3, you might lose a lot. Okay, so how much would you want to pick if you're in a group of 7 in this game? So if you are in a group of 7, you're playing for the first time, which number would you want to pick between 3 and 12? Yeah, so this table is purposely tricky. Let's try to decipher it. So I put some colors on it. So there is a very interesting divide between 7 and 8. Why is that? So if the group median is 7, you would rather want to pick 5. And if the group median is 6, you want to pick either 5 or 4. If the group median is 5, you would want to pick 4. And if the group median is 4, you want to pick 3. And if the group median is 3, you want to pick 3. So there is one equilibrium where everybody is picking 3. So the group median is 3, and you are choosing the best response. However, on the flip side, there's another one. So if it happened, the group median is 8. Now, instead of picking 8 or smaller numbers, you want to pick 10. And if the group median is 9, then you want to pick 10 or 11. If the group median is 10, you want to pick 11. And the group median is 11 or 12, you want to pick 12. So there's another equilibrium where everybody's picking 12, and you're happy for picking 12. So here, theory does not have a unique prediction. You have two predictions. One is everybody picking 3. The other is everybody picking 12. In fact, if you know game theory enough, there's another equilibrium where you mix. And we're not getting into that yet. So, okay. Anyway, so the problem is empirically what would happen. Okay, so here again, so the predictions of analytical game theory says that there are at least 2 pure Nash equilibriums. One is everybody picking 3, one is everybody picking 12. Of course, empirically, well, the only way to know is to actually run it. And the data shows that it's not the case that knowing there are 2 equilibriums, everybody goes to the good equilibrium where everybody's choosing 12 and earning above 100. It could be the case that this group, even after repeated play, you actually get stuck in the everybody picking 3, the bad equilibrium. And in fact, the short run, the initial choices, well, as some of you said, some of you wanted to pick 7 or 5 or somewhere between 7 and 5 and 8. Well, depending on where the initial sort of median is, well, you might go all the way down from lucky 7 all the way down to everybody picking 3, which is very bad. Or because everybody thinks that 8 is a blessing, is prosperity in Chinese, 一路发, and so now everybody starts with 8 and goes all the way down up to the good equilibrium. So here, what this means is that first, theory does not have a unique prediction, and so in addition to the theoretical considerations of equilibrium selection, you could have an empirical equilibrium selection in the sense of, suppose we play this repeatedly, so where would we end up? And also here, you could have this basin of attraction that if you start out on the wrong side of the Continental Divide, you might go this way to the bad equilibrium or that way to prosperity. Okay, so up to here, I've showed you 3 examples of what behavioral game theory is. So it's basically first asking what does the math say, then the question is what does the actual data say, and from here you ask the next step is to see if you can develop new theory to explain what you see in the data. Well, instead of so sort of inducing new theory, you could say other things. Well, you could say that, wait, theory is all wrong. That's a possibility. But usually the idea is not to say that theory is wrong. Well, all theory is wrong, but some theories are better than other theory. So the goal here is to improve theory, not to just say, oh, so theory is wrong. Well, end of the world. Yeah, that's the goal here. And however, one thing I do want to say is that for unfortunate reasons, this has not been the case of how game theory has evolved in the past, say, 50 years or even 60 years. This is evident from von Neumann and Morgenstern's quote, where they were talking about not having enough data back in 1944, and now we're like 70 years after, and we still don't have enough data. And so one possibility is that actually, John Nash actually did experiments himself with his co-authors at Rand. And unfortunately, John picked the prisoner's dilemma. So it's the simplest game that you can come up with, where there's a dominant strategy, which is to betray each other. And so there's only one Nash equilibrium, which is both defecting. And well, now we know why, but back then, apparently John was puzzled why people are not choosing to defect. People still cooperate sometimes. And so one possibility is that, well, initially you start out with this one experiment and find that this result completely disproves Nash equilibrium, because people are not choosing the only Nash equilibrium in this game. And so then people moved away thinking that, hey, maybe using experiments is not the right way to study this. And well, I think this is unfortunate, because now with enough data, we actually know what's going on here. Well, the main problem is not that game theory is wrong, it's that our assumptions about people being self-centered and not considering other people's preferences in this game is, this assumption is incorrect. Because people do care about, hey, if we both cooperate, then we could actually both benefit. Yeah, so maybe it's because of this. So we even in the history of game theory, we have went the wrong path. Had John Nash picked a different game, we could have been in a different equilibrium where we had experiments from the very beginning. But anyway, in any case, we are catching up now. So we have more and more experiments that come out and informing theorists to what is the right direction to develop your theory. Well, there could be other reactions to the data. Some people might say, wait a minute, people are confused. You're not motivated. Like, yeah, so in our classroom experiments, sometimes, like when I said, oh, well, I can't give you real money. I can only give you, say, this small chance of increasing your grade. Well, this may not be enough incentives for you to think carefully. Well, but first, this is an empirical question, right? If you think that giving you, say, $10 is not enough, then and 1,000 is what counts. That leads to an empirical test, right? If I run the same experiment, multiplying the payments by 100 times, and still the same thing, then I know that this concern is not valid. Of course, that is an empirical question, and it's very expensive to run experiments multiplying 1,000 times, but that's feasible, and people actually try that. Say they actually go to say poor countries or rural areas to actually run the same experiment, so that in real terms it's a lot of money, and to see if there's a difference. Next objection. Well, all experiments are designed, the design are all bad. Well, again, this is an empirical question, and there are worse designs and less bad designs. So, well, if you believe this is a bad design, you should be able to improve in the design and see that, hey, you get cleaner results. So again, this only calls for more experiments, not less. Next one. Hey, people are playing a different game. So in their mind, they're playing this mind game that's completely different from what you instruct them. The same thing applies to economic theory. Do you truly believe that in everybody's mind there's a utility function, and then you try to maximize this utility, taking the first order conditions, and then trying to calculate what is the optimal consumption, and hence I would buy 3 apples and 5 oranges? Well, unlikely. However, this does not mean that economic theory is all wrong. Oh, so now we should ditch the consumer problem calculation entirely. Why? Because even if this is an as-if situation, well, at least that's what you see in the behavior. And in fact, especially for policy reasons, this could be perfectly what you want. Why? Because when the government announces a policy, everybody misreads this to some crazy idea and then do some crazy behavior. But that's exactly what you want to know if you are a policy designer, how people would actually mistake or misread your policy. Because when you really want to do serious policy design, well, designing a perfect policy would not really work unless it's understood by all of the people. The last one is, hey, wait a minute. Oh, so you show people are irrational, but we can't model irrationality. Well, yes. So it could be the case that deviations from standard models are just complete noise. That's one possibility. However, if you see systematic deviations, then there's room to model things. So the question is this deviation just random, or is there some structure in it? In this sense, one of the best books I love is Dan Ariely's first book called Predictably Irrational. Unfortunately, the Chinese version got the wrong title. The Chinese version translated the title to be 谁说人是理性的, or Who told you people are rational? But the original English title was Predictably Irrational, which means that this seemingly irrational behavior is systematic, it's predictable. But what this means is that, well, if there are patterns in this irrationality, that means that there are, if it's predictable, that means there are some systematic patterns that you can model, that you can investigate and figure out what are these systematic deviations, and so how can we advance theory to explain these systematic deviations. Okay, so to conclude, I think I'll try to show this again and again, but basically what behavioral game theory is all about is to go, the starting point is always mathematical game theory or analytical game theory, showing you what the math predicts, and then saying, wait a minute, does the data confirm this? And then pointing to new direction of where the theory should improve. And so, yeah, and if you tell me, if you ask me, I would say, that's exactly what science, this is how science should advance. And if we're not doing that, then something's wrong about our scientific method. So we saw 3 examples, but basically the whole textbook is structured in this way. So we'll see games after games and the corresponding experimental results. And so this will conclude the first lecture, and I will move on to lecture 2.